थैंक यू। चलिए बेटा, आज जो है सिंपली सपोर्टेड बीम के ऊपर शेयर फोर्स और बेंडिंग मोमेंट के डायग्राम्स को स्टडी करते हैं। तो कैसे ड्रॉ करना है बेंडिंग मोमेंट और शेयर फोर्स ऑलरेडी हम कैंटिलीवर में देख चुके हैं। अभी जो है टुडे वी विल बी स्टडिंग अबाउट द एसएफडी एंड बीएमडी ऑफ सिंपली सपोर्टेड बीम। Now, first let us start with a simply supported beam acted upon by a concentrated load W at the center. Total span of the beam is L. If the simply supported beam AB is of span L and loaded with a point load W at the center, then how to draw the shear force and bending moment diagram? What is the shape you are going to get for this and how the shear force and bending moment is varying? Already मैं बता चुका हूँ आप लोगों को, for drawing the shear force and bending moment diagram we need the support reactions RA and RB. To calculate the support reactions, we will be using equilibrium equations. Support reactions RA and RB. Number one, algebraic sum of moments about A is equal to 0. If you take the moments about A is equal to 0, you take the moments, you take the upward forces moments as the positive, anti-clockwise, clockwise as negative. So the first force is RB upward, anti-clockwise positive into L, RB into L. If you move forward, there is a downward load W and the direction here is clockwise, minus W into what is the distance from C to A? L by 2 is equal to 0. Why? Because the moments, algebraic sum of moments at B at any simple support it is 0. So this implies RB into L is equal to WL by 2. L will get cancelled. This implies RB is equal to W by 2. And second equilibrium equation is algebraic sum of vertical forces is equal to 0. Sum of the upward is equal to sum of the downward. Upward, how many forces are there? RA plus RB. And downward only one load is there, minus W is equal to 0. This implies already we know the RB value. RA plus W by 2 minus W is equal to 0. This implies RA minus W by 2 is equal to 0. This implies RA is also equal to W by 2. So here we got the support reactions as RBW by 2 and RAW by 2. So after this we can easily draw the shear force and bending moment diagram based on these reactions as if you go for the shear force diagram, let us follow from the right side. If I follow from the right side, I will be following the thumb rule, run rule. Right side, upward force is negative. So first point is the support A, support B. Shear force at B is equal to minus RB. Since it is upward, that is equal to minus W by 2, RB value. And you all know the shear force between any 2 point loads remains constant. So you can say this is same just before C. Why? Because at C there is a point load. So second point is shear force at C is equal to earlier value is minus W by 2. There is a downward load here. So it is automatically positive. This is equal to plus W by 2. Is there any load? There is no load up to A. So you can say same up to A. So based on this, if you draw the diagram, this is the reference line, this is the B point, this is the C point, and this is the A point. At the B, it is minus W by 2. It remains constant here up to this. Immediately at C, it has changed from minus W by 2 to plus W by 2. And it is remaining constant up to A. So it is equal to your RA value. Already it has been tallied. So this is our shear force diagram. So from this diagram it is clear that already I told you, in the case of simply supported beam, the shear force will be maximum either at the left support or at the right support. So at both the supports you got the same magnitude, and you can say here by putting a star mark, maximum shear force is equal to W by 2, that is either at A or at B we got. So this is the maximum shear force from the diagram. In a similar way, let us see how to draw the bending moment diagram for this. First point is bending moment at B. You all know it is a simple support. At the simple support, the bending moment is 0. Next point is bending moment at C. So if you calculate the bending moment at C, you take the moment due to this as positive, that is RB anticlockwise positive, RB into L by 2, RB into L by 2, this is equal to W by 2 into L by 2, this is coming around WL by 4. And you all know bending moment at A, once again it is a simple support, the moment at A is 0. So from this figure, it is clear that this is A, this is C, this is B. You all know whenever there is a point load in the cantilever beam, we have seen the shape of the bending moment diagram is linear. So here it is B, at the B it is 0, at the A it is 0, at C the height is WL by 4, what you got. So if you join these two by straight line, total it is positive. Why? Because simply supported beam bends like this. So this is a sagging moment. If it is having convexity at the bottom and concavity at the top, then such type of bending is called as sagging bending, which is positive. In the cantilever, totally we have seen hogging. The bending was like this. This is a cantilever beam. The bending was like this, having convexity at the top, concavity at the bottom. It was negative, which was named as hogging. It was negative. But in the case of simply supported beam, it is a sagging bending moment, totally positive moment, and this is your bending moment diagram. From this total bending moment diagram, it is clear that the bending moment is maximum at the center. So maximum bending moment, that is equal to bending moment at C, that is equal to how much is the value? WL by 4. You have to remember this value. Whenever there is a maximum, whenever there is a point out at the center, the maximum bending moment is WL by 4 and maximum shear force is W by 2. These are very, very important objective questions which you will come across in your competitive exams. So these are the two diagrams, how the shear force is varying from right hand to the left hand or left hand to the right hand, with which the maximum is W by 2. In the same case, this is the variation of the bending moment diagram from left hand to the right hand with a maximum of WL by 4 at the center. Let us go for multiple point loads. Means next question, when a simply supported beam is acted upon by 2 or 3 loads, let us say this is one case, but for this case also you remember it will be an important objective question for you. Whenever there is earlier in the earlier problem, the point load was acting at the center, but suppose if the point load is not at the center, somewhere at a distance of small a and small b distance from the right support, let us say the total span is L. Now what is the shape of the bending moment diagram and shape of the shear force diagram for this case? So same case, you all know. First, the basic thing is you need the support reactions. The first step is support reactions. So taking moments about A is equal to 0, start with the right support, RB into L, downwards load minus W into small a is equal to 0. So this implies RB is equal to WA by L. In a similar way, if you use the second equation, algebraic sum of upward is equal to algebraic sum of downward forces. So you will get upward as positive RA plus RB minus W is equal to 0. But you know already the RB value, that is WA by L is equal to, this is minus W is equal to 0. This implies RA plus, take the LCM as L. Here it is WA by L, and when you come across this value WA minus W into L is equal to 0. This implies RA plus W into, here it is minus W, A minus L divided by L is equal to 0. But we know A plus B is equal to L. A plus B is equal to L. This implies A minus L is equal to minus B. If I substitute this in the above equation, I will get RA minus WB by L is equal to 0. This implies RA is equal to, I will get it as WB by L. So one support reaction is WA by L, यानी यहाँ पे RB के पास what is the value I am getting? W into the other distance by L. If I talk about reaction at A, W into the other distance B by L. These are the two support reactions what we got as per the equilibrium equations. Now based on this, we got the final values. RA is equal to WB by L. RA we got it as RB we got it as WA by L. These are the two support reactions what we got. Now let us calculate the shear force diagram. Let us draw the shear force diagram. So first, shear force at B, upward, positive, minus RB. What is RB? Minus WA by L. Next, shear force at C. At C, there is a downward load. So minus WA by L plus W. So this is coming to W into L minus A by L. But A plus B is equal to L. This implies L minus A is equal to B. So what is shear force at C now? If you substitute here, it is WB by L. Is there any load from C to A? There is no load from C to A. So it remains constant, same up to A. So if I draw the diagram, this is B point, this is C point, this is A point. So at B, the value is WA by L, constant up to this. Immediately it has increased to WB by L and it is constant up to A, which is equal to your RA. So this is our shear force diagram. I hope everyone got it. Just by following the simple thumb rule, if I start from the right side upward is negative, and whenever I get a downward force, it is a positive force. So based on this is a shear force diagram. From this, it is clear that since B is greater than A, your maximum shear force is nothing but either at A or B, na? So B is greater, na? B is greater. That's why your shear force at A will be equal. So what is the maximum shear force? Either it should be WB by L or WA by L. But since if you compare this A and B here your B is greater than A. So automatically your support reaction at A will be higher when compared to the support reaction at B. That's why your maximum shear force is nothing but the support reaction, which is equal to RA. So this is the maximum shear force. Now let us go to the bending moment diagram. If you start from the right side, bending moment at B is 0, since it is a simple support. If I calculate the bending moment at C, you all know it is RB into small b. RB into small b. What is the RB value? WA by L into B. This is equal to WAB by L. Next, bending moment at A, it is 0 since it is a simple support. So if I draw the diagram, this is B point, this is C point, and this is A point. At B it is 0, at C the height is equal to WAB by L. Here it is 0, join these two, join these two. You will get an eccentric triangle, not a concentric triangle here. So this is bending moment, and from the total bending moment diagram it is clear that the maximum bending moment is under the load and its value is equal to WAB by L. You can note it as Mx, that is equal to WAB by L. This is the maximum bending moment what you are seeing from the shear force diagram, bending moment diagram, and maximum shear force is WB by L since B is greater than A. Either it should be WB by L or WA by L. But when you compare these two, your B value is greater. That's why WB by L is the maximum shear force out of this, where you got it at support A. Let us go to the next question. Let us work out with multiple point loads. Let us say at C, D, E, 3 point loads are acting 5 kilonewton, 10 kilonewton, 8 kilonewton loads are acting at a distance of 1 meter, 1 meter, 2 meters, 1 meter. So what is the total span here? Total span is 5 meters. So we are with simply supported beam AB of span 5 meters acted upon by 3 point loads. 5 kilonewtons are 1 meter, 10 kilonewtons at 2 meters, and 8 kilonewtons at 4 meters from the left support. We have to draw the shear force and bending moment diagram for this. So as I told you in the previous lecture, first on one half of the page you draw the beam diagram and draw the extended lines below that, such that it will be easy for you to draw the shear force and bending moment diagram. Now to draw the shear force and bending moment diagram, you all know once again the basic thing is support reactions. Support reactions RA and RB. So first equation is sum of the moments about A is equal to 0. RB into total distance is 5 minus downward load 8 into 4. From 8 to A is 4. minus 10 into, what is the distance from 10 to A? 2 meters, minus 5 into 1 is equal to 0. This implies RB into 5 is equal to, all will be positive if you shift it to the right side. First 32 plus 20 plus 5. It is coming to 57. 52, 57. So therefore RB is equal to 57 divided by 5. 11.4. What is the value of RB? 11.4 kilonewtons. Next is second equation, sigma y is equal to 0. Sum of the upward minus sum of the downward, 5, 10, 8 is equal to 0. RA plus 11.4 minus 23 is equal to 0. This implies RA minus 23 means 21.6. So 23, you have to deduct it from 11.4 here. So it is 11.6 is equal to 0. This implies RA is equal to 11.6 kilonewtons. RB value is 11.4 and RA value is 11.6 kilonewtons. So now based on this, you can note down here RB 11.4. After calculating, you can write down here 11.4 and 11.6. Based on these support reactions, we can easily draw the shear force diagram as number 1 point. Shear force at B, you all know it is minus RB, upward force. So minus 11.4, you all know it remains constant just before E. I need not write that. At E it changes. At E is equal to, earlier value is 11.4, downward load is plus 8, to minus 3.4. Next, at D, earlier value is minus 3.4 plus 10, 6.6 kilonewtons. Next, C, earlier value is 6.6 plus 5, it is coming around 11.6 kilonewtons. Is there any load up to A? No load. It remains constant up to A and automatically this should equal to same up to A and its value is equal to, already you got the RA value as 11.6. So now if I draw the diagram, this is B, this is E, this is D, this is C and this is A. So at B it is 11.4. So just before E it remains constant. At E it has reduced to how much? 3.4. It remains constant here up to this. Immediately it has changed to 6.6. It remains constant here. Immediately from 6.6 it has increased to 11.6 and remains constant up to A. So this is your total shear force diagram. Now if you check out from this shear force diagram, it is clear that once again the maximum shear force is either at support A or at support B. It is nothing but at support A, I am getting the maximum shear force which is equal to 11.6 out of this total diagram. So just I can write maximum shear force is equal to RA, that is equal to 11.6. That's why in my previous discussions already I told you, you need to draw all this. If it is an objective question, what is the maximum shear force means, just here to compare the support reactions, whichever is having the maximum, that is taken as the maximum shear force. So here it is RA. if I draw the bending moment diagram, bending moment at B is equal to 0, bending moment at E, RB into 1, that is equal to 11.4 into 1, that is equal to 11.4 kilonewton meter. Next, let us go to the next point. Bending moment at D means start from the beginning. RB into 3 minus 8 into 2 minus 10 into 0. This is equal to 11.4 into 3 minus 16. 12, 1, 4. 34.2 minus 16. 18.2 kilonewton meter. Next, bending moment at C. For your convenience, you can do another, you can calculate in another way, like you can start from the left side. Bending moment, why? Because C is nearer to A. What is bending moment at C? Once again it is upward, RA into 1. Simply it is like that. You can calculate like that also. RA into 1, that is equal to 11.6 into 1, 11.6 kilonewton meter. And you all know the bending moment at A is 0, since it is a simple support. Now if I draw the diagram, bending moment diagram, A, B, where it is 0, 0, this is C, this is D, and this is E. What is bending moment at E? 11.4, height is 11.4, at D it is 18.2, at C it is 11.6, at A it is 0. So if I join simply by straight line, why? Because these are point loads, the bending moment diagram is linear. So this is your bending moment diagram. When you compare the values, max is equal to, where you are getting the maximum bending moment? At D I am getting MD, that is equal to 18.2 kilonewton meter. So from the total figure, from the figure it is clear that the bending moment is maximum at the point D and is equal to 18.2 kilonewton meter. Now let us work out for the complete UDL. Now we have gone through the multiple point loads. Next is, let us discuss about total UDL, W per meter, and if the span is L, what is the shape of the bending moment diagram, what is the shape of the shear force? Let us see. This is center A. As all at the center also you can draw the line. So first basic thing is reactions. In my previous lectures, already I told you, whenever you come across the UDL, please you show the resultant of the UDL where it is acting. As I told you, that this is the UDL intensity, uniformly distributed load, which is common throughout the span, which is called as UDL, and the span is intensity is W. Why for it is? For 1 meter the load is, UDL intensity is, for 1 meter the intensity of the load is W kilonewton. And what is the total span? Total span is L. For L meters, what is the load? W into L, which is called as capital W. This is your total UDL. And what is this small w? Intensity of UDL. This implies I can say capital W is equal to small w into L. And where it will act? At its center. जितना भी UDL का लेंथ है उसके सेंटर पे एक्ट होगा, यानी at the center which is represented by capital W, that is equal to small w into L. Small w into L. And as already I can give another clue here. Since there is only one load acting and that too it is at the center, it is called as symmetrical load. Whenever there is a symmetrical load, your RA, RB, whenever the load is symmetrical किसको बोलते हैं? When can you call a loading system as a symmetrical system? When the left half is equal to the right half. Means when the left half is the image of the mirror image of the right half, then you can say that it is an symmetrical load. So in that case, your RA will be equal to RB, that is equal to total load by 2. What is the total load here? Capital W by 2. It is nothing but small WL by 2. So if the question is, what is the maximum shear force in this case? Your answer should be either RA or RB, which is nothing but WL by 2. So simply you can write here, maximum shear force is nothing but WL by 2 in terms of intensity, or in terms of total load, you can say it is capital W by 2. Please try to differentiate between small w and capital W. Capital W is the total UDL and small w is the intensity of the UDL. So now, anyhow, I got the RA, RB values as WL by 2. Sidewise I can note down WL by 2. WL by 2. Now let us calculate the shear force. Shear force at B minus RB, that is equal to minus WL by 2. Next, shear force at C minus WL by 2 plus total UDL is there plus WL, that is equal to, it is coming to WL by 2, and is there, it means WL by 2, and you can say what is shear force at A. You can use your rule. Left side, na? What is the shear force? If you start from the left side, LUP rule. Right side, run rule. If you start from the left side, LUP means left side upward force is positive. So it is nothing but plus RA, that is equal to WL by 2. Shear force at A is WL by 2. Sir, here the total load, here it is plus WL by 2 minus WL. Why for? At C it is plus WL by 2. At B it was minus WL by 2. When you come up to C, in between B and C, there is a load of, for 1 meter it is W. This is the length of L by 2. So your load will be WL by 2. So your load is WL by 2 here, plus WL by 2. So at B it is minus RB. When you reach the C point, there is no point load, just you concentrate on the UDL here. So what is the equivalent load acting for this portion? For 1 meter it is W, for L by 2 it is WL by 2. So earlier minus WL by 2 plus WL by 2. It is coming to 0. 0 at the center. And automatically what is the shear force at A? You can check it. Either you can follow this or this step, or you go back to this shear force at A. Previous value was 0 at C. But in between C and A also there is a WL by 2 load. Am I right? Between C and A there is a WL by 2. So when I am coming from the right side, I am coming from the right side. So at B it was minus WL by 2. At C you got it as 0. At A. So 0, previous value was 0. Downward force is plus WL by 2. So it is coming to WL by 2, which is same, or you need not write down as you got the previous value. Either you calculate like this directly from the left side, or from the right side also you can finish off your journey up to this. So what is the shear force at A? Plus WL by 2. So if I draw the diagram, this is B, this is C, and this is A. At B it is WL by 2, at C it is 0, at A it is plus WL by 2. So join kariye. So this is negative, this is positive. So from the shear force diagram, it is clear that the maximum shear force is nothing but WL by 2. This is the maximum shear force, which is nothing but your support reaction. Already I told you in the beginning, the maximum shear force will be either RA or RB. In this case, both are same. That's why your maximum shear force is WL by 2. Next is bending moment diagram. You all know bending moment at B is equal to 0. Next, bending moment at C. Now you can see when you calculate the bending moment at C, first you start from the right side. RB into L by 2. Next load is this load, and what is the distance from this half UDL? Half of L by 2 na? If this is L by 2, what is the distance of this portion UDL from C? It is acting at the center of L by 2. That's why it is half of L by 2. Half of L by 2. So I can say RB into L by 2 minus WL by 2 is the load, and the distance is half of L by 2, the distance. So this is coming around, your RB value is WL by 2 into L by 2 minus WL by 2 into L by 4. This is coming to WL square by 4 minus WL square by 8. If I take out the denominator, I will get it as WL square by 8. And next is bending moment at A. It is 0 since it is simply support. So out of these values, if I check out, at B it is 0, at A it is 0, at C I am going to get the maximum ordinate, maximum height as WL square by 8. And already in the previous case in the cantilever, I told you whenever there is a UDL, the shape of the bending moment diagram is second degree parabola. Already I have shown you for the UDL. So how to join these 3 points? You join by a curve. You join by a curve which is nothing but second degree parabola. This is your bending moment diagram. Therefore, maximum bending moment is equal to कितना है बेटा maximum bending moment? WL square by 8, which is a very very important bit objective question. So let us see with the simply supported beam with partial UDL, यानी UDL पूरा लेंथ नहीं है, थोड़ी लेंथ तक है, तो तब shear force diagram, how to draw the shear force diagram when the UDL is not for the full length. Let us say the UDL is partially like this, and there is a point load here D. UDL is of say 2 kilonewton per meter, and it is acting for a length of 3 meters. Let us say this gap is 1 meter and this is another 1 meter, and let us say this is 10 kilonewtons. Total span is here 5 meters. Now we are supposed to draw the shear force and bending moment diagram for this beam. Here, how is the loading? Here, how is the loading? The loading is partially UDL here for partial length, थोड़ी length के लिए UDL है, और उसके बाद point load अमल कर रहा है यहाँ पे. तो for this case, how to draw the shear force diagram? Let us see, 1 second. हेलो
जी
क्या जी, क्लास में हूँ मैं, क्लास में हूँ।
अच्छा पायल बात कर बोलती कि 11 बजे तो
हाँ चलो ठीक है
फोन कर लो। सुनो जी तुम्हें 25 मैं
हाँ चलिए बीच में अभी I think it is clear. So now here it is partial UDL for 3 meters and a point load 10 kilometers is acting at a distance of 1 meter from the right support, and the UDL is for 3 meters from the left support with an intensity 2 kilonewton per meter. So we have to draw the shear force and bend moment diagram for this. So before this, as you know, support reactions are the first basic thing what we require. Let us calculate the support reactions which are named as RA and RB. चलिए first one is sigma m about A is equal to 0. So first let us start from the right side. RB into what is the total distance? 5. Downward load minus 10 into 1 plus 3 4 minus I already told you the UDL is acting for a length of 3 meters. You draw the equivalent UDL as for 1 meter it is 2, for 3 meters it will be 2 into 3. And what is the distance it will be from the left support? 3 by 2. So RB into 5 minus 10 into 4 minus this UDL is 2 into 3 into 3 by 2 is equal to 0. This implies RB into 5 is equal to 40 plus 9, 49. Therefore, RB is equal to 49 by 5, 9.8 kilonewtons. RB is equal to 9.8 kilonewtons. So, similarly, the second equilibrium equation is sigma y is equal to 0, RA plus RB minus downward is 2 into 3 minus 10 is equal to 0. This implies RA plus 9.8 minus 6 minus 10 is equal to 0. This implies RA minus, this is a minus 0.2, 6.2 is equal to 0. This implies RA is equal to 6.2 kilonewton. Now you can easily say out of these two support reactions which is the maximum 9.8. So therefore objective question is maximum shear force is equal to RB, that is equal to 9.8 kilonewtons I can say. Just by seeing the support reactions I can say the maximum shear force is RB value which is equal to 9.8. So you can write down here 9.8. Here it is 6.2. What I got? Now let us draw the shear force diagram. Shear force at B minus RB, that is equal to minus 9.8 kilonewtons. Is there any load up to D? No load. Same. Just before D. Next, shear force at D. Previous values 9.8. Previous value is minus 9.8. बात मत करिए बेटा बीच में. Previous value is minus 9.8 plus at D there is 10. That is equal to 0.2 kilonewtons. Same up to C, there is no load up to C. Then you can say shear force at A is equal to previous value is 2.2 plus there is a downward load plus 2 into 3, that is equal to 6.2 kilonewtons which is equal to your RA. Which is equal to RA. So now, if I draw the diagram, this is B, this is D, this is C, this is A. So at B, the value is 9.8, remains same up to D. Immediately at D, it is changed to 0.2. 0.2, from 0.2 it is increased to 6.2. Sorry. Here it is 0.2 here. Point D, point C, point A. Up to D, it is 9.8 minus, and immediately it has changed to 0.2 at D, and this 0.2 is common up to C. From 0.2, it has increased to 6.2. So, this is the shape of the shear force diagram. Once again, the shear force diagram, from the shear force diagram, it is maximum at B point, already I told you. So therefore, maximum shear force is equal to RB, that is equal to 9.8 kilonewtons. So we have to draw the bending moment diagram for this. Bending moment at B is equal to 0, simple support. Next, bending moment at D, RB into 1, that is equal to 9.8 into 1, 9.8 kilonewton meter हो गया, because the moment due to W is 0 at D. Next point, bending moment at C, first, once again from the beginning, 9.8 into what is the total distance? 2 minus 10 into 1, 18.6 minus 10, this is equal to 8.6 kilonewton meter. Next point is A. You all know bending moment at A is 0. Bending moment at A is 0. So if I draw the diagram, B, this is D, this is C, and this is A. It is 0 at B, 0 at A, and at D, 9.8. At C, it is 8.6. Here it is 0. But in between C and A, there is an UDL. So you will get a curve from here to here, a straight line. And then here it is a straight line. So this is second degree parabola, and this is linear. Why? Because there is no UDL between C to B, so it is a straight line. So out of this, the maximum bending moment is, therefore maximum bending moment is equal to 9.8 kilonewton meter. This is the maximum bending moment. And this is your BMD. Now let us go for the next problem. That is same simply supported beam. Let us take the UDL for the full length, and 2 point loads are acting here, or let us say 1 point load is acting at a distance of 2 meters, and let us say this is 3 meters, and this load is 10 kilonewtons. Let us say the UDL is of 2 kilonewton per meter. Now the problem is a simply supported beam of span 5 meters is acted upon by a UDL of intensity 2 kilonewton per meter for the full span and a point load of 10 kilonewtons at a distance of 2 meters from the left hand. So we are supposed to draw the shear force and bending moment diagram for this. So let us say this is RB, this is RA. As I told you, whenever there is a UDL, you draw the equivalent point load for this UDL. For 1 meter it is 2. For 5 meters it will be 2 into 5. Why? Because for total 5 meters it is acting. What is the distance from the left support? 5 by 2. So how many loads are there on the beam? 2 into 5 and then 10 kilonewtons load. 2 loads are acting. So now first one is support reactions. Number 1, algebraic sum of moments about A is equal to 0. RB into 5 downwards minus 2 into 5 into 5 by 2. Next is 10 kilonewton minus 10 into 2, it is equal to 0. RB into 5 minus 25 minus 20 is equal to 0. This implies RB is equal to 45 by 5, 9. RB is equal to 9. Second equation, sum of the upward is equal to sum of the downward. RA plus RB, downward is 10 minus 2 into 5 is equal to 0. This implies RA plus 9 minus 20 is equal to 0. This implies RA minus 11 is equal to 0. This implies RA is equal to 11 kilonewtons. So as you know, once again the maximum shear force is nothing but greater of the two support reactions. Therefore I can say maximum shear force is equal to RA, that is equal to 11 kilonewtons. So if I draw the diagram, this is B, this is C and this is A. So at B I got it as 9. Okay, I just have to calculate now. This is support reactions. Afterwards let us see what to be done. So RB I got it as 9 and RA I got it as 11. Now let us see how to calculate the shear force first of all. First, shear force at B minus RB, that is equal to minus 9. Now here I want to concentrate on one very important point, that is when you start from B, your next point is, it is obvious, it is C, but before moving to the C, you can see how many loads are acting. UDL in between B and C and point load. 2 loads are acting at a time. Here, it means 2 loads are combining at the C. So for that what you have to do is, already I told you in the cantilever, you calculate just before C. Why? Because this UDL you will be getting. What is this UDL? 2 into 3. Why? Because this is for 3 meters. And at what distance from the C? It will be 3 by 2. Is it clear? So what you have to do is shear force just before C is equal to previous value is minus 9 and there is a downward load in between B and C equal to plus 2 into 3. So it is coming to minus 3 kilonewtons. Next you can write at C. Shear force at C is equal to previous is minus 3 and there is a downward load plus 10. It is coming to 7 kilonewtons. Next you go to A, you can directly start from left side at A. Shear force at A is, you can use Lap rule. Left side upward force is positive. So that is equal to plus RA, that is equal to, how much we got? 11 I think, 11 kilonewtons. 11 kilonewtons you got. So now, if I draw the diagram, At B it is minus 9. Just before C it has gone to minus 3, 9 to minus 3, and at C it has increased to 7, and by reaching A it has gone to 11. So this is your shear force diagram. I hope it is clear for you. Shear force at B is minus 9. Just before the point C it is minus 3, but at C immediately it has changed to minus 3 to plus 7, and automatically you know the shear force at A is, if you start from the left side you can use Lap rule. Left side upward is positive, so at A it is equal to RA. Simply you got the 11 here, you got the 7 here, you can join it by a slope line, and from minus 3 it has gone to 7 and it has increased to 9. This is your shear force diagram. Now if you go for the bending moment diagram, bending moment at B is equal to 0. Now you can calculate directly at the bending moment at C is equal to 9 into 3, 9 into 3, downward load is minus 2 into 3 into distance is 3 by 2. That is equal to 27 minus 9. It is 18 kilonewton meter. And you all know bending moment at A it is 0. So if I draw the diagram, B, A, 0, 0, here at C it is 18. Since UDL is for the total span, you have to join by a second degree parabola. Total is second degree parabola. Here the value is 18. This is our bending moment diagram, which we are getting the maximum bending moment at C. Another is here the total span is 6 meters. Let us say the UDL intensity is 2 kilonewton per meter. Here it is 5 kilonewtons. This is 10 kilonewtons point load. Here the total beam is of 6 meter span acted upon by total UDL. UDL for the total span as 2 kilonewton per meter, and a point load of 10 kilonewtons at 2 meters from the right end, and a point load of 5 kilonewtons at 1 meter from the left end. And for this case, we are supposed to draw the shear force and bending moment diagram. So first thing is RB, RA. So first is support reactions. Number 1, algebraic sum of moments about A is equal to 0. But better for the support reactions, you calculate the total UDL first. A bigger discontinuous line. For 1 meter it is 2, for the total is 6. So it is 2 into 6, please. This equivalent UDL is meant for the support reaction first. So at what distance it is acting from here to here? 6 by 2. So how many loads are there on the beam? One is 10 kilonewtons point load, another is 5 kilonewton point load, and a total UDL of 2 into 6 at 6 by 2 from the left hand. Now it will be easy for you to calculate the support moments here, support reactions. RB, first is RB into 6 minus 10 into, what is the distance from 10 to this? 4 minus this UDL 2 into 6 into 6 by 2. Next is minus 5 into 1 is equal to 0. Now it becomes easy for you to calculate the support reactions. RB into 6 minus 40 minus 36 minus 5 is equal to 0. RB into 6 is equal to 81. Therefore, RB is equal to 81 by 6. This one's a 6, 18. Approximately 13 point, say this is 13.5. Approximately you take it as 13.5. So next is sigma y is equal to 0. RA plus RB downward is minus 5 minus 2 into 6 minus 10 is equal to 0. This implies RA plus 13.5 minus 5 minus 12 minus 10 is equal to 0. This implies RA, this is coming to 20 to 27, 13.5 minus 13.5 is equal to 0. RA is equal to 13.5 kilonewtons. So here both are same. RB as well as RB, RA and RB value, we got the values of RA and RB as same. So based on this you can decide what is the maximum shear force. Already I told you, greater of the two, it is nothing but both are same. So what is the maximum shear force in this case? From the objective point of view, it is 13.5. So let us mark with a circle here, reactions, 13.5. Now let us go to the shear force calculations. Let us start from the right side. Shear force at B is equal to minus RB, that is equal to minus 13.5 kilonewtons. Already I told you, when you go to the point D, you are getting in between D and B UDL as well as 10. That's why you split up the equivalent UDL of this small part. What is the equivalent UDL, please? For 1 meter it is 2. It is acting for 2 meters. 2 into 2. What is the distance? 2 by 2. Right. So at B it is minus 13.5. But what you have to write? Just before D. Why? Because point load is also there. It is minus 13.5 downward plus 2 into 2. Minus 9.5 kilonewtons. Next, shear force at D is equal to previous is 9.5, downward there is a 10 plus 10. It is 0.5 kilonewtons. Next, when you move to the C, once again in between you are getting a UDL here. So, what is that UDL? 2 into 3. What is the distance? 3 by 2. So, shear force just before C is equal to previous value was 0.5 and there is a downward load plus 2 into 3, 6.5 kilonewtons. Now you can write at C is equal to 6.5 plus there is a downward load 5. 11.5 kilonewtons. Next is, last is A. You can directly go to A. You need not calculate before A. In between this, there is a load of 2 into 1. And what is the distance? 1 by 2. So now at A it is 11.5 up to C, and in between plus 2 into 1. So this is coming to 13.5 kilonewtons, which is equivalent to your RA value. Already we have calculated RA. You should get the coincidence with the RA value, 13.5. So now if I draw the diagram, this is B, this is D, this is C, and this is A. At B, I got it as minus 13.5. Just before D, it is 9.5. Immediately, it has increased to 9.5 to 0.5 at D. And just before C, it has increased to 6.5. At C, it has increased to 11.5 due to this point load. And just by coming to A, from 11.5 it has increased to 13.5. This is your shear force. So already I told you, when you go through this total shear force diagram, your maximum shear force is nothing but either at A or B, both we got it as same, that is equal to 13.5. Now, let us draw the bending moment diagram. Bending moment at B is equal to, once again it is 0 at simple support. Next is bending moment at D. How many loads are there? RB into 2, downward load minus 2 into 2 into 2 by 2 na? 2 into 2 into 2 by 2 at D. So what is RB? 13.5 into 2 minus 4. This is 27 minus 4, that is equal to 23 kilonewton meter. Next point, bending moment at C. Start from the beginning. RB into 2 plus 3, 5. RB into 5 minus this UDL minus 2 into 2 into what is the distance from here to here? 2 by 2 plus 3. Now it is easy for you to calculate. Next, let us come to this point load. Minus 10 into 3, minus 10 into 3, right? Next is, in between C and D there is a UDL. Minus 2 into 3 into what is the distance from here to here? You are calculating at C, 3 by 2. So that's why better to draw these small UDLs also, equivalent UDLs, so that it will be easy for you to calculate the bending moments at various points. Once again I am repeating, bending moment at C. RB into 5, right? Next, this small UDL, 2 into 2 into what is the distance up to C? 2 by 2 plus 3, 2 by 2 plus 3. Next is this point load, minus 10 into 3. Next is this small UDL between C and D, 2 into 3 into 3 by 2. So this is equal to, what is RB? 13.5 into 5 minus 4 4s are 16 minus 30 minus 9. So this is equal to 5 4s are 25, 15, 67.5 minus 46, 55. This is coming to 12.5. And as you know, the bending moment at A is 0. Now, if I draw the diagram, this is B, this is A, this is C, and this is D. So at B it is 0, at A it is 0, at D 23 I got, at C I got it as 12.5, here it is 0. Since the UDL is for the total length, you have to join by a parabola. Total diagram is second degree parabola plus, so maximum bending moment is what? Out of this total diagram, we are getting the bending moment at D as the maximum bending moment, that is equal to 23 kilonewton meter. So, what is the final conclusion we are going to make out after going through this diagram? When we started the journey from B to A, after drawing the total bending moment diagram, out of this we are getting the maximum bending moment at D, whose magnitude is equal to 23 kilonewton meter. Agar aapko, if it is asked in the objective question, what is the maximum bending moment for this, like this, for example. So, first step is you have to calculate the support reactions, and then you calculate the bending moment at C and D and check it with the total diagram. You need not draw the diagram, just you compare the values. At B it is 0, at A it is 0, whatever you are going to get at D and whatever you are going to get at C, compare these two values, and whichever is the maximum, that is your maximum bending moment. So from this, the maximum bending moment is 23 kilonewton meter, which is a sagging moment, positive moment at point C. Let us say this is the last problem of this. Let us take the UDL not starting either from the left support or from the right support. Let us say it is starting after a distance of 2 meters from the left hand and 1 meter from the right hand. And let us say this portion is for UDL portion is 3 meters and the intensity of the UDL is 2 kilonewton per meter. The loads are, point loads are at its extremities. This is say 5 kilonewtons and this is say 8 kilonewtons. Now what is the total span of the beam here? The total span of the beam is 6 meters. Total span is 6 meters. And there are 3 loads. One is 5 kilonewton, another is 8 kilonewtons, and then UDL is there. For 1 meter it is 2. Show the equivalent load for this portion. 2 into 3. Why? Because the UDL is for a length of 3 meters here. 2 into 3. From its extremities, from its ends, either from the left hand or from the right hand, both are same. It will be 3 by 2. So how many loads are there? One is 5 kilonewton, another is 2 into 3, total UDL, another is 8 kilonewtons. Now we are supposed to draw the shear force and bending moment for this. Let us say this is RA and this is RB. So first one is support reactions. First equation, as usual, sum of the moments about A is equal to 0. Start from the right side. RB into what is the total distance from B to A? 6 meters. Proceed further. There is a load of 8 minus 8 into what is the distance from 8 to A? 3 plus 2, 5. Next, UDL minus 2 into 3 into what is the distance from this load to this support? 3 by 2 plus 2 minus 5 kilonewton into what is the distance? 2 is equal to 0. This implies RB into 6 minus 40 minus 2.5, sorry 3.5, 6 into 3.5. 21 minus 10 is equal to 0. This implies RB into 6 minus 71 is equal to 0. RB is equal to 71 by 6. 6. to the 12, sorry, approximately you can take it as 12 kilonewtons. 72, you will take it as 22, 72 to 12, you take it as 12. Next is, second equation is sum of the upward is equal to sum of the downwards. RA plus RB, sum of the upward. Downwards forces are minus 2 into 3 minus 8 is equal to 0. This implies RA plus 12 minus 5 minus 6 minus 8 is equal to 0. This implies RA 11, 19 minus 7. RA is equal to 7 kilonewtons approximately. Now you got the RB as how much here? 13 plus 6, 19, 12 plus 7, 19, right? So you got the RB value as 12 and RA as 11. Now if the question is an objective question, what is the maximum shear force in this case means, as I already told you, it will be either of the support reactions, either RA or RB. Out of these two, RB is maximum here. I can put the star mark and as I can write, maximum shear force is nothing but RB, that is approximately equal to 12 kilonewtons is the right answer. So anyhow, RB we got it as 12 and RA we got it as 7. Put it in the circle. Now let us draw the shear force and bending moment diagram for this. Let us start from the right side. Shear force, that is the run rule. Shear force at B, right side upward is negative, minus RB, minus 12 kilonewtons. Is there any load up to D? No load. It is understood that it remains same just before D. But what is happening at D? Minus 12 plus 8, minus 4 kilonewtons at D. And when you move further, when you move to the next point C, here you are getting UDL and point load. That's why it is your duty to calculate just before C. Just before C. Previous value is minus 4. Downward is plus 2 into 3. It is coming to 2 kilonewton. Next you calculate shear force at C. 2 plus 5 is equal to 7 kilonewtons. Now are you seeing any load from C to A? So it means that it remains constant from C to A and automatically this is same up to A, which is equal to your shear force at A, and that is equal to your RA value. Am I right? What is the RA value? 7. So it will get coincided with that value. So if I draw the diagram, this is B, this is D, and this is C, and this is A. So at C, at B, I got it as minus 12 and it is remaining constant just before D. At D, it has reduced to 4 and just before C, it has increased to plus 2. It has gone from minus 4 to plus 2. This is plus 2, this is minus 4, and at C it has increased to 7, remaining same up to A, 7 kilonewtons. Positive, this is negative. So this is the variation of shear force from when you start your journey from right hand to the left hand or left hand to the right hand. So out of this, the maximum shear force is being seen at the B. That's what I wrote you in the beginning. While calculating the support reactions, the maximum shear force is nothing but RB value 12 kilonewtons. Now here you are coming across one very important point, salient point. That point is the shear force in between C and D, it is changing from minus to plus or plus to minus. So this point, let us name it as X. What is this point? This is the point where the shear force is changing its sign, or you can say point X is point of zero shear force, I can say. What is point X? Point X is the point of zero shear force. Keep in mind, remember already I told you in the beginning. So wherever the shear force is zero, there you can expect maximum bending moment. वहाँ पे bending moment की value ज़्यादा से ज़्यादा होती है वहाँ पे, जहाँ पे भी shear force zero होता है. ज़्यादा से ज़्यादा means you'll get maximum bending moment at X. Let us see that bending moment diagram also. But before going for the bending moment diagram, it is our duty to locate this point X. इसको बताना पड़ेगा कि C and D के दरमियान X कहाँ है? Where is that X? So to locate the distance of this X in between C and D, you have to draw these two similar triangles. We can work out from the similar triangles. So what should I give here? Star mark. Location of point X, which is nothing but point of zero shear force. For this, I have to draw the diagram here. What is the left side value? 2. What is the right side value? 4. This is C, this is D. This is the point X. Now, what is the total distance between these two? Total distance between C and D is 3 meters. If I name this as X, this remaining distance will be 3 minus X. So the base of this small triangle is X and the base of the bigger triangle is 3 minus X. So base by height is equal to base by height. From similar triangles, चलिए बेस करिए. X by 2 is equal to 3 minus X by 4. 3 minus X by 4 is equal to X by 2. This implies if you cross multiply, 4X is equal to 6 minus 2X. 6X is equal to 6. X is equal to 1 meter. From C, point C. तो point of zero shear force कहाँ आ रहा है? You are getting the point of zero shear force at 1 meter from left end, and automatically from the right end it is 2 meters. This is the point X location. Now let us draw the bending moment diagram. Bending moment at B is equal to 0. First point. Next point, bending moment at D, as usual, RB into 1. RB is 12 into 1. You are getting it as 10 kilonewton meter. Next point is don't go to C. In between C and D, you are getting X here. So what you draw is, you draw the free body diagram here. RB is 12. From the D point, from the D, there is a load of 8 kilonewtons. This distance is 1 meter and you are getting an UDL. This point is X. What is the distance from D? The distance from D is 2 meters. So now what is the intensity of the UDL? You know the intensity of the UDL is 2. So it is 2 into 2. And what is the distance from X? 2 by 2. This is the free body diagram of the portion XB. Why? Because I have to calculate the bending moment at X. Bending moment at X, I can say it is as maximum bending moment. Max is equal to, start from the beginning, 12 into 1 plus 2. 12 into 1 plus 2. Downward, minus 8 into 2. Minus 2 into 2 into 2 by 2. Am I right? Once again, I am repeating. I am calculating the bending moment at X, which is nothing but maximum bending moment. 12 into 3, 1 plus 2, minus 8 into 2, minus this total UDL is 2 into 2 into 2 by 2. So let us see, 12 3s are 36, minus 16, minus 4. 16 kilonewton meter is the Mmax. And now you calculate what is bending moment at C. Now I'll tell you one point here. You can start from the left side. You need not start from the right, because if you start from the right side, if you continue from the right side, it is a lengthy one. You can calculate from A also, if you start from the left side, what is bending moment at C? Simply RA into 2. That's it. Simply bending moment at C is RA into 2. What is RA value? 7. 7 into 2, 14 kilonewton meter. And you all know bending moment at A is 0 since it is a simple support. So if I draw the diagram, B, D, C, A. At B it is 0, at A it is 0, and at you have to locate the X also. This is X. So bending moment at B is 0, and what is bending moment at D? 12. What is bending moment at X? 16. What is bending moment at A? It means C, 14. Here it is 0. Now tell me, the UDL is in between C and D. So whatever the portion is there in between C and D, if I join the points, that should be parabolic. The remaining is, there is no UDL here. So is there any load UDL from A to C? No UDL. So A to C straight line. And from B to D also there is no UDL. It is once again a straight line. But in between these two there is a UDL. So you join a curve like this. So this is linear. This is also linear. And this is second degree parabola. So this is what your bending moment diagram is saying. With the maximum value as, what is the maximum value? I can say at X, Mx is equal to Mmax. So your maximum bending moment is 16 kilonewton meter. So I hope everyone got the idea how to draw the shear force and bending moment diagram, and also whenever you come across a salient point like where the bending moment shear force is changing its sign, so there you can expect the maximum bending moment and how to calculate it by drawing the free body diagram. Better you draw the free body diagram, separate it from X to that B, draw separately that portion of the beam, and then you calculate. It will be easy for you to calculate the maximum bending moment. I hope it is clear for everyone.